Welcome back. We're in lesson 64. Let's talk about domain for just a little bit. In problems in mathematics, in physics, chemistry, and other mathematically based disciplines also, numbers can be used as replacements for the variables. And they're often restricted by the nature of the problem or the type of problem that we have. Let's say if a person goes to the store with 25 cents to buy eggs. And let's say that eggs cost 10 cents each. The total amount of money that can be spent on eggs can be represented by the equation here. Total cost is equal to the 10 cents per the number of eggs, right? We can see that. If 10 cents is the value, the number of eggs times 10 is going to give us how much we can spend or expect to spend on eggs. So if we had, let's see, for A, if we had 0 eggs were bought, and for B, if 1 egg was bought, and C, 2 eggs were bought, we could just simply say that our cost is equal to 10 times 0 in this case, which would equal 0 cents because we didn't buy any eggs, so we didn't spend any money on them. For B, our cost would be equal to 10 times 1, which would be 10 cents because we bought 1 egg. And here it would equal 10 times 2, which would be 20 cents because we bought 2 eggs. We cannot use 3 as a replacement because the buyer only has 25 cents to spend. We can't use 2.5 because you can't buy half an egg, right? So it's specific to this problem because our person who's going shopping only has 25 cents. You can't buy a half of an egg. So the only values that are possible in this solution set is that they buy no eggs, that they buy 1 egg, or that they buy 2 eggs. That's all they can do. And we couldn't use a negative number because she's only got 25 cents with her. She's not bringing eggs to give back, right? You can't go to the store with money and not buy eggs and get more money back. That's just not the way it works. So we are restricted by the statement of the problem to using only these whole numbers 0, 1, and 2. The set of permissible replacement values for the variables in a particular equation or inequality is called the domain. So these 3 numbers right here, that equals our domain. And a domain is just, like I said before, the set of acceptable replacement values, or not necessarily acceptable, but permissible, the ones that could be there, that, feasibly could happen given a certain set of conditions. So in this set of conditions, she either bought none, 1, or 2. That's it. That's all she could do. So let's look at some other scenarios here. Since every equation and every inequality has a domain, and since this is an important concept, it's customary in algebra to include problems in which the domain is specified. These problems should help with the concept of domain. We'll use the capital letter D as a symbol for domain in this course. And we will indicate the domains as sets by enclosing them with braces. So the domain for this problem we just did is 0, 1, and 2. Okay, that's our set, and D is the letter we use for domain. So our domain is 0, 1, and 2 for this previous problem that we just did. I'm also going to illustrate that D, the domain is illustrated as reals that means a real number system, all the real numbers. And D here is also illustrated as positive integers. If I can get my curly bracket to do right, there we go. The domains specified here are the numbers 0, 1, 2, the set of real numbers, and the set of positive integers. In the problem sets, if a domain is not specified, it should be assumed to be real numbers. We know real numbers include all the numbers, whether they're rational, irrational, positive, negative, whatever. So unless it specifies what that is, it's this one, right? Unless it gets real specific, right, we always assume it's all the real numbers. So let's look at an example problem. We are asked to graph in 64.1, we're asked to graph x is greater than 2 and the domain is equal to real numbers. So what that means is we can graph all the real numbers that are greater than 2. So we come up here on our graph, we find the number 2, right? Just like that. And there's no equal sign, so we don't fill in the circle. And then we just go this way, because this way is greater than 2. That's how you graph that. Easy peasy, right? Okay, I'm going to take this and I'm going to say, oh, that's not what I wanted to do, sorry. Let's see if it'll let me do this. Nope, wrong thing. It didn't let me do it. I am trying really hard to get rid of this for you. Okay, there it goes. Alright, so let me pull up another number line this way. I know I can do it this way. If I just, there we go. If I just drop it in. Aha, that worked perfectly. Alright, so let's do another one. In this one, we have 64.2. And this says to graph that x is greater than or equal to, it is, oh, sorry, not greater than or equal to 3. And the domain is going to equal integers. So it's just whole numbers, right? It's not, oh, excuse me. You see this line up here? Real numbers. So real numbers includes the numbers in between the integers. The integers are just these numbers. So if the domain is integers, then it can only be the numbers themselves. So if x is not greater than or equal to, you only have 3 options. You have greater than, you have equal to, and you have less than. So if it's not greater than and it's not equal to, then x must be less than 3. And it's only the integers. So we're going to say, we're going to find 3 right here. And we are going to, there's nothing we can do here because it's not included. We're not drawing a line. So x is less than 3 in the integers, so that's going to be 2 is less than 3. That's an integer less than 3. 1 is an integer less than 3. 0 is an integer less than 3. -1, -2, -3, -4, -5, -6, they're all less than 3. And then I'm going to do my arrow here just so it's clear that it goes on and on. So x is not greater than or equal to 3 means that x is less than 3. So I can't put a dot on 3 because 3 is not included. It's every integer because of this, every integer less than 3. So the domain affects how we graph these lines and this information. If it says real numbers, then that means it includes every number in between. If it says integers, it's just the number itself. And so we only put a dot on just the number itself. All right, so let's try another one. Let's erase all of this. And let's try a couple more. Wrap our heads around this a little bit better. All right, so let's try red this time. 64.3. We have, it says to graph that x is greater than or equal to -1, and our domain is equal to reals, so real numbers. So all the numbers, right? Because a real number system is all the numbers. So if x is greater than or equal to -1, the first thing we do is we find -1 and we circle it. Okay, because that's the number that's called out. And we see that it is greater than or equal to, so we can fill it in. And the reason we're right on top of the 1 is because we know that our domain is going to include the line because it's every number. So we're just going to say that x is greater than or equal to -1. We're going to go to the greater than side and fill that in just like that. And that would be the answer to that one. 64.4 says that x is less than -1. And our domain is equal to positive integers. That's all we can use. So if x is less than -1, right, and it's positive integers, anything less than -1 is going to be a negative. And if our domain can only be positive, then our answer is going to be null. We have a null set. We have no answers to graph. There's nothing we can do. So the answer, when you have a situation like this, the answer is just this circle with a line crossed through it. Or you could say the word null. Okay? Those are two correct answers. All right, what if we have, let's say another one. All right, so 65.5. Let's say we have x is greater than or equal to -5, and the domain is going to be equal to positive integers. Again, positive integers, right? So what that means is that x is going to be greater than or equal to -5, but the answers can only be positive. Okay, so what's the first positive integer that's greater than -5? This one. Then you have this one, and then you have this one, and this one. So basically your domain is going to be all positive integers because they're all greater than -5. That is all we can do for that. All right, so let's talk about something else. I hope you can see kind of how the impact that this has on your answer and how to graph it, okay? So the domain matters. Look at the domain before you start looking at what to graph, so you know whether or not you need to start at the number that's given or find the number that coincides with the domain first. All right, let's clear this. Let's talk about the additive property of inequality. The additive property of inequality says that if a, b, and c are any real numbers such that a is equal to b, okay, then that means that a plus c is equal to b plus c, right? And c plus a should be equal to c plus b. If a and b are the same value, we should be able to substitute in a and b for either one. That also means that if a is equal to b, then a plus c is equal to b plus c, where also b plus c is equal to a plus c. So what that literally means is that I could also say, okay, let me take b out and put a in. So a plus c would be equal to a plus c, and b plus c would be equal to b plus c. And then a plus c would be equal to b plus c. I mean, it's like you're saying these two values are the same. The only thing that's different is that we're adding c to both of them. All right, so it's just a substitution situation. And it should be something that is common sense for you. It should make sense. You should be able to say that if a is equal to b and a is equal to 2, then logically it follows that b must be equal to 2. That's basically what this whole thing is about. It's saying if I tell you that these two are equal, and then I give you the value for one of them, you should be able to sub in that same value for the other one. That's what this part of the lesson is all about. Being able to recognize equal values within an equation based on information that you are given. And it's important that you should be able to do so. It's called drawing conclusions and logical thought process. So let's look at number 64.6. All right, I need another graph. I'm going to pull it back up here. Here we go. There it is. And our problem says that he wants us to graph x plus 2 is less than 0, and our domain is going to be the real number system. So reals. Okay, so all the numbers. All and any of the numbers. So that means we're drawing on the line, okay? So if x plus 2 is less than 0, then how do we figure out what x is and how to graph it? We treat it just like this were an equation. So we subtract 2 from both sides. Okay, that cancels this. I don't know what that did, but we're going to ignore it. X, therefore, is less than negative 2. Now, doesn't that make sense? Because if x, let's see, where are we at? Yeah, if x was anything other than negative 2, then this wouldn't be less than 0. Right? X has got to be less than negative 2. So if this is negative 3, then negative 3 plus 2 is negative 1. Negative 1 is less than 0. Okay? That's how you solve for that. X is going to be anything less than negative 2. So we circle negative 2. Let me use a different color. We'll circle negative 2. It's not equal to negative 2. It's just less than. And then we go this direction. So any number less than, because this could be, x could be negative 2.1, right? So negative 2.1 plus 2, that would be negative 0.1 is less than 0. And it is. It is less than 0. So you have to include all the numbers right up to 2 because they're all less than 2. Okay? So let's look at another one. Let's look at 64.7. And this says x minus 3 is greater than or equal to negative 5. And the domain is going to be equal to, there should be a semicolon, sorry, integers only. So that means, looking at the domain, that we are not going to graph on the line, we're just going to put dots on numbers. Okay, that's what that means. So we have to solve this again. So we're going to add 3 to both sides because we need to find out what x is by itself. So this cancels. This becomes x is greater than or equal to negative 2. So if x is greater than negative 2, let's find negative 2. There's negative 2. It's greater than or equal to, so we can sub it in. Or we can fill it in, sorry. So if x is greater than or equal to negative 2, we're going to go to the right. Now let's pick a number on our line over here and see if that is correct. We'll sub it back into our original problem, which was x minus 3 is greater than or equal to negative 5. Let's pick positive 5 because it's over here in this set of numbers. Let's see if it works. So 5 minus 3 is greater than negative 5. Let's 5 minus 2, or I'm sorry, 5 minus 3 is 2. 2 is greater than negative 5. So that's correct. All right, well, what about negative 2? Let's pick the very number we started with. Let's see how that works. So if x minus 3 is greater than or equal to negative 5, and we put negative 2 in here, right, negative 2 minus 3, that's negative 5, is actually equal to negative 5. So that's also correct. So that's why we started with negative 2, and we included every number to the right because these are all greater, and when we sub in any one of these numbers on the number line, it is going to give us a true statement. And that's the whole point of graphing this. We are looking for the statement or the range of numbers that gives us a true statement here. And you can check that by picking any one of these numbers and subbing them in after you've graphed it, just to make sure you went the right direction. Because sometimes, you know, we draw it in the wrong direction. We're in a hurry. We're not thinking. Check your work. You'll see where you've made your mistake if you do that, and then you won't mess up so quickly. And that is the last example problem we have for lesson 64, so I will see you in lesson 65.